So, we have seen state charts, the history mechanism, and how StateMet evaluates a state chart. Okay. Now, all through our discussion, we have assumed that events are being generated, that event is being evaluated in some way with conditions, but how are these events passed? There are, so essentially, since it is a communicating finite state machine, there are multiple finite state machines, they are communicating among themselves. So, we know that two modes of communication are popular. One is message passing, another is shared memory, right. Now, in state chart, we use broadcast mode of communication. Okay. In terms of implementation, what does it mean? It means that if from any state, I am in some state and some event I generate, suppose this was an event and I take some action, and this action A1 is actually generate an event, generate event E2. Then this E2, event E2 is visible to all other states, okay? To all other states which might be waiting for some other event E3 taking some action, all right, some other state which is might be looking for E2, some other state which is not looking for E2, it will be visible to all. That means what? It is a shared memory mode of communication, just like a global memory, right, not only for the events, but also for the variables. Okay, for the variables as well as the events, whenever there is a change or in generation of an event, that is visible to all. Okay. So, when the StateMet is executing, then it can see all those variables, it is looking like a global variable set, right. Events and variables are being treated in the same way. So, that is a very important aspect of state chart, that it is a broadcast mode of communication. We will later on see that there are other modes of communication as well, which are not broadcast mode. So, here is an example of a broadcast mode of communication. Say here, let us look at this. There is a state A B. So, A and B are two AND states, that means both of them are active. Now, an event E takes place here, and that is visible to this one also. Therefore, that event is also visible here, and both of them make a transition. So, if at the particular status, remember the status, step thing, suppose in a status is A1 B1, that means here I am in A I am in A1, in B I am in B1, and event E occurs, then both of them are visible. So, in that step what will happen? We will compute the event E and we will see what will be the next step. In the third step of execution, our status will be A2 B2. Okay. Here is another example. Say I am in state A1 and an event E takes place. So, I have entered A2. This entering A2 is again an event, because this is being treated as an event here. You can read this, that is entered A2. Therefore, B1 Suppose my initial status is A1, B1, then E has taken place. Then in that step, what will happen? In that step, it will be E2, my state will change to A2, and then A2 B1 will be the status. And as I entered A2, my status changes. Next cycle, it will become A2 B2. Clear? Here is a third example. Here it is no longer an event, but data. You can see that here I am again, my state is A1 B1 and X is 0. On an event E, I come here. So, the next status is A2 B1. Here I carry out some assignment. Still that is not reflected in the next cycle. It will be seen that here it is X is equal to 1, then my state will be A2 B2, because this event is on data X1. Okay. So, that is what is meant by broadcast communication, and this is also in a way handling with the synchronization, which we will see soon. Pardon? C, where? Oh, B and C, these two are equivalent. No, just a minute. This here, what is being shown is that the event of entering A2 will enable this transition. Here, this X is being set to 1, may be internal within, after some actions have been done in A2, then this is being set, and as this is being set, then it will be done in the next cycle, this one will be enabled. Okay. So, they are not exactly equivalent. One is on entry, another is on assignment. The other example, another issue that comes up with state chart is a conflicting scenario like this. Say, I am in a particular state, where on A is shown that I am making a transition, and it is also shown this. What will happen? In these scenarios, if that is a specification, then this specification is ambiguous, but statement does not stop you from making such specifications. If this specification is done, then we cannot guarantee that the implementation will give you determinate result, because some implementation can take a precedence of an internal transition, another can give the precedence to an external higher level transition. Similarly, another example could be that I have got two states. I am saying x is less than 20, you make this transition, and here I say x is greater than 10, you make this transition. Right. Now, suppose these are concurrent transitions or whatever. Now, obviously, you can see, looking at these values, x is greater than 10 will certainly do this, but now when x is 15, then this can also take place. So, these are some conflict scenarios which do not allow us to ensure, to guarantee that state chart will always give me deterministic or determinate results. Okay. Now, what are the pros and cons of state charts? The pros are, number one is hierarchy. Hierarchy allows us arbitrary nesting. There is no limit on that. I can go on nesting one state and there can be two states under this, and this state can be further decomposed into two sequential states and another state. All these things are possible. Any arbitrary nesting is possible, and thereby we can reduce a complex scenario into comprehensible specifications. We can look at different phases and can understand it much more nicely and proceed accordingly. The second thing is StateMate. A tool is available, and that StateMate has got very clear semantics defined. Very clear semantics is defined. Therefore, I can have an executable specification. Okay. There are others like StateMate, StateFlow, beta state. There are others also, say beta state, StateFlow. All these are commercial tools, but StateMate semantics is very nice and very clearly researched. And we have got backends. That is very important. We must have backends that will take our state chart, all right, state chart, and translate it into software or hardware languages. Why did I say software and hardware languages? What is the meaning of this software and hardware languages? By that I mean state by state chart. It is not the case that I can use it for specifying embedded systems alone. I can specify any complex software also using state chart, and so from that I can generate the software by some automatic software generation tool. The specification of the language state chart can enable me to specify complex software as well. Also hardware, embedded hardware, as we have seen the answering machine example, we can have many such, and state chart can therefore be translated into some hardware description languages. As I said that, like VHDL, Verilog, there is a hardware C, there is another very popular language, System C, which are variants of C with some special constructs. And from here, let me spend a little time on that. So, what can happen is that I have got a state chart specification. I can directly synthesize from state chart to some architectural implementation. That is our objective, or I can compile this state chart into VHDL, say, or say System C, and I have got some CAD tools which can take VHDL, and I can have the implementation through synthesis, right. So, I can do that. That is an advantage, and another important advantage is state chart is very suitable for distributed applications. For example, you are working in a automobile industry and you want to develop some embedded solution, and there might be distributed processors at different corners of your car which will be communicating, and some event occurring here should trigger some other event occurring somewhere else. That can be easily captured in state chart. Why? Because state chart uses the broadcast mode of communication. Okay? That is a very salient feature of state chart. So, therefore, using this we can very nicely capture distributed applications.
What does direct synthesis of state chart mean?
If you have got some CAD tool, now from this state chart what will happen? It can come to some intermediate code. You need not, you have got some tool, say tool 1, say cadence tool, okay, which takes VHDL and produces architectural implementation, or Verilog and from there does it. Verilog also can be used in cadence actually, but I think Verilog is used. But here suppose from state chart, from this graphical thing, you can generate some intermediate code yourself, and you can design a synthesizer which can take this in, not these commercial tool of cadence or synopsis, right, but you can have separate tool which will take this intermediate code generated from state chart and will generate the synthesis, sorry, not here, generate the synthesis, right. That is possible, because whatever you are stating here is a language. Through a language you have specified the requirement, and you can show that in the form of a graph, and from using that graph you can, if you have got that tool, you can do that. That is possible. Now, what about the cons of state chart? It is I just now said that it is useful for distributed applications, but some people are contesting that often that is not very much applicable for distributed applications. All the broadcast mechanism is there. So, therefore, we are not hinging much on that, but one of the major cons of negatives of state chart is no programming constructs are there. Programming are not there, sorry. Programming constructs are not there. It is all graphically, we go on bringing down to the state machine level, and everything I have to describe in state machine level. All right. But say for example, I write a sorting program. Now, it is much easier, suppose I am doing some sort, or I am doing some finding the max or whatever. That particular thing can be better expressed using programming constructs than using state machines. By state machines, it becomes really very cumbersome and meaningless. So, that is a limitation, big limitation of state chart. And non-functional behaviors. Behaviors cannot be stated. For example, I say that this entire part of the task must be completed max within this time. Okay. We have got timer construct saying that that's the delay or how long it can be here, but it's a non-functional, not associated with the behavior, that for this entire task graph maybe will have to be completed within say 10 millisecond. That is that specification is not embedded in the state chart. It can be kept in a separate file. Okay. And the generated programs, when we generate, that may be inefficient, but those things are less important. But one of the major things that we will try to circumvent in a later phase, maybe in today's lecture if time permits, that the programming constructs are not there. Okay. Now, we have seen many desirable features of our specification languages. We have already taken care of through state chart hierarchy and concurrence, right. But there are some other issues which need to bother about. One is synchronization. Okay. Now, because the concurrent processes we are showing, okay, fine, that these processes are, or these states or whatever actions, these are concurrent. But concurrent processes are often not independent. They run concurrently up to a level, but at some points they need some handshaking or they need some synchronization. Okay. Now, there can be two types of synchronization. One is control dependent synchronization, another is data dependent synchronization. Okay. So, I will show you an example of different types of synchronizations. So, here is a control dependent synchronization example, right. Here is a behavior X, some behavior, this behavior. Now, one is by fork and join. We know fork join constructs, you know from your operating system course. Begin Q, fork A, B, C, join. In this language structure, we can do that like here. So, this is a graph where using fork and join, we can create processor and we can join here. Let us look at synchronizations, how synchronizations are taken care of in state chart, how you can achieve that. This behavior A, B, C, you enter this, that means you enter A, enter B and enter C. Now, when an event E occurs, now these two I have got no control over the relative speed of this process. So, at a particular point of, and also I do not know about these events. So, at a particular point of time it can be ABC can be in state A, A2, B1, C2 or anything. But I want to synchronize them and want to bring them to ABC. So, if the event AE occurs, that is I am exiting from the super state and re-entering the super state, that means again as I re-enter, I am going back to this A1, B1 and C1. So, that is one mode of synchronization. Another mode of synchronization is that suppose I am in A1 and I want to come to and this one is in B2, say I want A2 B2 to be the state and then I may, or B1 A2 to be the state. So, if I make an exit from here and enter A2, then forcibly I am entering A2, no history, nothing, I am just forcing it here and it is not default. This one is a default state, but here I am not keeping it as default, it is forcing it here wherever it is B1, wherever it might be. As soon as I exited this also got exited, this one also got exited because I exited the super state. So, it will become B1 A2, all right, because as it re-enters it is default and this forced. Therefore, in that way also we can do some synchronization. Data dependent synchronization is usually done through shared memory. Okay. Now, talking of data dependent, that means what? What is data dependent synchronization? Something is going on it's proceeding nicely. It's a data flow graph. Some data is available and some these are operations. Operations are taking place. Now, here I want to wait till here in another part of the thread some data are being produced, and I want that this will proceed only after some data is produced here. So, I can create a data dependent synchronization between these two threads, right. So, typically that sort of data dependent synchronization that can be because of common data. This one is using a common data that can be done through shared memory. So, whenever I am what is being meant by that? That means this operation, this task is suspended till the other part produces some data, that means comes up to a particular level. So, that can be a common event that this data is ready, I can visualize in that form, or it can be a shared memory that here I am waiting for some data that will come in the shared space. So, that is possible. That is, data dependency can be done using shared memory, or I can also do it using message passing. We will show both. Message passing can again be of two types. One is blocking and non-blocking. Blocking means whenever I pass on a message, that message until that message is received by the receiver, the sender will not proceed. Okay. That has got the advantage that no data will be lost, because suppose there are two processes communicating through the same buffer, some queue or something. Say there is one process P1, another process P2, and there is a queue, and this one is sending in the queue and this one is receiving from the queue. Now, suppose this process is slower and you have sent it in the queue and that has not been consumed, and this is very fast, it may be the queue will be full and soon you will start losing data from here, right. So, by blocking, what we do is once the data is consumed, I send the next one. What is the disadvantage of this? The disadvantage of this is the entire P1 is being held back, so the performance will deteriorate. Non-blocking means I will not wait for the signal that my data has been received. So, such message passing can also be used for data dependent synchronization. Here is an example of data dependent synchronization. You can see again this, actually this one we had shown earlier when we were explaining the broadcast mechanism. So, here you see again the data dependent synchronization. One is the same event, both of them are synchronized. Here some state, this one is data driven synchronization. So, as this data comes here, I make this transition. So, this was made to wait till process A reaches A2 and makes x to be 1. Okay. That is also data dependent synchronization. So, synchronization is another pardon? Last one is event driven. Last one is control dependent. Yes, this one is, it has entered over here and based on that some event has taken place. Another important thing that we need to look at is behavior completion. How do you know that, say whenever I am actually describing a behavior in my state chart, right. I am actually describing a behavior. There can be 3 different parallel processes and this is doing something, all right, maybe But when does the thing ends? When does it end? That is not very clear from here. So, how do we depict when a particular behavior has completed? Each of them are behaviors. I have described the behavior as a complex behavior has been decomposed into 3 smaller behaviors. But when does it complete? Because when one completes, is must be other behaviors should be able to detect it, right. So, other behaviors say A, B, C must detect when some behavior has completed. Why is this important? This is important because in hierarchical specification level, I can view the subsystems as independent modules. Each of them is an independent module, and they do not know directly from each other, and they are being developed independently. So, unless I know that this has completed, I have got no, unless it is explicitly told, I have got no other way to really understand that this be whether one has completed or not. Now, how can this be represented? One thing is, in FSM, all of you know how the completion of a behavior is shown, the final state. In programs, how is it known? The last statement. Okay, or return in a procedure, right. So, or even say in C, when you give this last main reaches the end bracket, then we end, right. So, somehow, so a C program and another process are going side by side. Now, whenever this reaches an end, then or a return, then a return value is sent. So, at the global point, if I am continuously looking, if I am looking at that, and I know that this part has completed, clear. But and in the state chart form, we have got no scope of doing that, but there is another way, that is I am diagrammatically showing you. We will come to this maybe in the next lecture. That is a program state machine, where we use, there are some other features. You can extend that to your state chart also, that another graphical notation of this square blocks here. What is being shown in this diagram is the final state for an FSM. All right. So, let us look at this first, this diagram. Looks like a state chart, the hierarchy is there, this is 1 and then I break it down. So, it enters x1, you can see a small block here, this one I am making it a little bigger, so that is visible, that whenever this reaches this black box, that means it is a completion, it is a completion of x1, and this transition means, now it is transition is label D1. Now, that means even before completion, if E1 comes, it can come over here. This is another transition, or if these two are connected, then this means a different thing. This means that if event E1 comes and the behavior of x1 has reached the completion, then only come to x2. Here, this E2 is meaning something different. E2 is meaning that whenever E2 is occurring, you come out of E2, and come out where? Come out at the completion. This completion is whose completion? This the completion is the completion of the whole thing, right. Let us look at here again. Now, this is much more nicer. I have got the entire behavior B, which has got two behaviors x and y. X has got x1, x2, x3. Now, x1, these are normal transitions. This is a transition on completion. When E1 occurs and if x1 has completed, I will come to x2. This is just this same behavior. Here, what is happening? From y1 on event E3, I come to y2. What is this? This means, see, there are no events associated. As y2 completes, you complete y, and as you complete y, you E4 is generated, E4 and E4. You have completed y, but E4 has not taken place. So, you have not exited, the whole thing has not completed. So, this means the semantics is that okay, y2 has completed. Here y2 has completed, obviously, otherwise I would not be here, and E4 has taken place, I come here. Look at this edge. What does this edge signify? I have come here, x2 has completed, that means x has completed, but I have not gone out. I am going out on this completion, and E5 I am entering y. Now, this is what is used in program state machines, okay, which has got some more flexibilities over state chart, which we will do in the next class. Okay. So, this one brings us to the behavioral completion. In that way, we can show the behavioral completion. Obviously, that will be useful for communication among the finite state machines.